So here our objective is to analyze a plane stress problem, which is a thin plate with a hole, and see the hole is centrally placed within a plate. The hole is centrally placed within the plate, and here, so this is, the hole is centrally placed within the plate. Now and it is subjected to uniformly distributed load at both the right and left ends. So this is x, y, and now you notice that if you take this line, this is a line of symmetry, and so is this line, and when you stretch the plate, this is also known as a plate stretching problem. When you stretch the plate, the deformation in this direction will be 0, and so this line can move only in this direction, but it cannot move in this direction. So this cannot move in this direction. So here ux on this line, ux is 0. Similarly, this line cannot move in this direction, cross. This line cannot move in this direction, cross. So this uy is 0 on this line. So now instead of analyzing this full plate, we can analyze only 1/4 of the plate, and we apply a unit distributed load of unity intensity, 1 Newton per millimeter, and this length is 100 millimeter and this length is 200 millimeter, and the thickness is unity. So if you in ANSYS, automatically it will be taken as unit thickness for plane stress problems. So let us start doing it in ANSYS. Okay, so preferences, structural as usual, preprocessor, element type, add, edit, delete element type, add. So here solid and quadrilateral 4-node element, the element number is 182, quadrilateral 4-node, close. So this element, no real constants are required, so material properties are required. So material models, structural, linear, elastic, isotropic, and here the values 2e5 in Newton per millimeter square. The length is given in millimeter and the pressure is given in Newton per millimeter, not pressure, the intensity of the uniformly distributed load is 1 Newton per millimeter. So Newton for force and millimeter for length. We are using consistent units. So material properties over, section not required, modeling. So create, here we will be creating areas and rectangle first by 2 corners. So by 2 corners, so the left corner is at 0, 0, the width being 100 or width being 200 and the height being 100. Okay, the rectangle is created, and then areas, we create a circle, a solid circle. The center is at 0, 0, this is 0, 0, and the radius is 10. We create a circle with radius 10. Okay, the circle is created, and now we'll create part is over. We'll go to operate. In operate, there are several options, so we'll go to Boolean and subtract. So subtract areas. So the first set of areas from which the second set has to be subtracted. So the first, here both the first set and the second set, they consist of only one area. So the first set consists of this rectangle, so okay, and the second set consists of this circle. Okay, so this is subtracted. So operation part is over. Now the geometric modeling is done, and we are going to finite element modeling. So we'll be using mesh tool, and let us bring a mesh tool here. let's close this. So mesh tool, so we'll be using smart sizing and we'll use the finest. So the left end is the finest and the right end is the coarsest. So mesh areas, and it will be a free mapping using quadrilateral element. So mesh is looking for picking of area which has to be meshed. So we pick this area and it is meshed. So yes, plane 182 may misbehave in bending, so there may be some locking phenomena, but for the time being we ignore that. So close. The mesh is created. Now the load has to be applied. So loads, analysis type is obviously static. So define loads, apply structural. So first of all, structural pressure. So on nodes, so here we'll have to select all these nodes. So instead of picking one by one, so what we can do, we can make a box selection, and box left corner, box one corner and diagonally opposite corner, and all the nodes are selected. Okay, and the pressure value is constant, and let us give a constant value of -1 because we want a uniformly distributed load acting outward, not on the element but on the other direction. So okay, so load has been applied and it is being shown by a pink line, but it's better to go to plot control, symbols, and show pressure. Instead of face outlines, you show it with arrows and it will be clearer. So now we have to give pressure part is over, displacement on nodes, but here the nodes are very closely arranged, so again you better zoom. So mesh tool, the purpose of mesh tool is over, so you better close it, and here you box zoom this part. Okay, so this part is enlarged, so now zoomed. So now you apply structural displacement on nodes. Suppose you select these nodes, okay, and you give ux. Okay, so this nodes ux is given, and now on nodes, so 1 2 these nodes, okay, and ui. So applied, so bring it a little down, yes, and again on nodes you select these nodes. So the critical nodes are now selected, you give ux, yes, so applied. So I think, and now also again on nodes you select. So the closely spaced nodes are already selected and constrained. Okay, so now you can fit. So the rest of the nodes can be selected by box pick. Oh sorry, so box pick. Rest of the nodes can be selected by box pick. Okay, so UI, so over, and here on nodes box pick. So okay, ux, okay, so it's done. So it's time to solve. So close all these, close all this, and go to solution, solve. So for that analysis type you should check new analysis, static. Okay, so go for solve current load step. Okay, solution is done. Okay, now you have to go to post processor, get read results, only one set. So first set read, plot results. Deformed shape you can check. So deformed plus undeformed. The white dotted is undeformed and the blue is deformed. Or you can go to contour plot, nodal solution, x component of stress. Okay, so this is x component of stress. So this is the region of all the happenings, all the stress changes. So again you can pan, zoom, rotate, box zoom, and you can have a better view of this. So this is what we get. So the red is 3 and the far field stress is 1, and the far field stress this color. So this color, no, not this color, this color, and this color is close to 1. So 3 we are getting as stress concentration factor. Now what we can do, you can just go to path operations, because if you want to plot the stress value over a given path, then you can do it. So define path, and by location, so first you have to give a name of the path. So my path 1. So it is defined by 2 points because it's a straight line which you are going to define. So 2 points are sufficient, and let these default values remain. So okay, so point number 1 has coordinate of 0 0 0. Okay, and point number 2 has a coordinate of 0. Suppose we want it up to 50 on this line. So from 0 0 0 to 0 50 0. Okay, so what you can check the defined paths. So my path 1 is the path defined, and current path, so it is defined from 0 0 0 to 0 50 0. Now you have to map onto path. What you have to map? The variable of interest. So our Sx is meant the variable of interest, so you have to map it here, and it is mapped. Okay, so here some interpolation points do not lie on the selected elements because we have taken, why it is coming. So plot path, let's plot the path. So the path is from here to here, and from here to the circumference of the circle. So no elements are there, that's why that warning is coming. So let us make a small modification. So in the path operations, first let me delete the path. So by name, so we are deleting this path. So this path is now deleted. So path is deleted. Now we are again defining the path by location. So the name we are keeping same, it is again using 2 points. So okay, so the first point location, instead of making it 0 0 0, so previously we made it 0 0 0, we are making it 0 10 0 because it is starting from the circumference of the circle. So okay, and 2 is same as before, 0 50 0. Okay, the same thing we did, only so current path is 0 10 0 to 0 50 0. Okay, now the path is defined. Now the next operation is map onto path. So Sx, okay, so we have mapped on the path. Then path operation, plot, sorry, not plot, plot path means this path is plotted from, this is the first point and this is the second point. Then plot path items. So on graph means on a graph you will see the plot. On geometry, that means on this geometry itself. So on geometry if you do, so Sx is automatically selected with a scale factor of 100. So you do it and you get this plot. So the value here at the circumference of the circle is 3 times the far field value, and this is the stress concentration. Or what you can do, you can plot on the graph Sx. So this is, so at the circumference which will be 0, that is 0, 10, 0 point is 0 and 0 to 40. So this is the stress concentration. So this is this.